Assalamu alaikum. In this series, Mr. Omar will guide you through some practice problems to cover all items included in the coverage issued by Emirates Schools Establishment, E.S.E. This is part 5. Have a fruitful time.
Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome back to part 6, I think, by part 5. Okay. Now we are to discuss something about Kirchhoff law for junction and loop and how can we analyze such a circuit. Question 1. Consider the circuit and these values R1, R2, R3 and so on to find the following. Let us put the values on the graph or diagram. R1 2 ohms, here is 2 ohms. R2 3 ohms, 3 ohms here. V1 5, this is 5 volt. V2 12 and R3 4 ohms. Find the current passing through V1. For such a circuit, it couldn't be simplified to one circuit with a power supply in series and parallel. So we will go to Kirchhoff rules. Here we have 2 points A, B. Let us name the other C, D, E, and F. We can follow the directions in the circuit. For the first loop, 1, this is the first loop, and this is the second loop. These are 2 loops. And for junction rule, we have only 2 junctions at A and B. First, let us find or apply the Kirchhoff junction rule at A. Kirchhoff junction rule at A. Here A, this is A1, I1 and I2, both are going into A, while I3 going away from A. This is I3, this is I2, here is I1. Now, summation I in equals summation I out. So I1 plus I2 equals I3, and we can put it in this form: I1 plus I2 minus I3 equals 0. This is our first equation. Now apply Kirchhoff loop rule, voltage rule, on I need the first loop, this one, starting from D, C, then A, B, D. Summation I, R equals summation VMF. First, let us check the currents and their resistance. The current from D to C, it is I1, is the current, but there is no resistance between D and C, so there is no potential drop between D and C. From C to A, this branch or this segment, I1, it is entering R1 and it is going to right, and the analyzing here up, then right, then down, then left. So it is with the direction of the analyzing. So it should be positive. So I1 R1 plus, continue the path from A to B. We have R3 and I3, and it is in the same direction of the analyzing. So it is positive, I3, R3. Now from B to D, there is no resistance, and we finished at the starting point, which is D. Now we can check for the electromotive forces. First, the electromotive forces for V1, it is from D to C, and for V2 from F to E, from the negative to the positive terminal inside the battery. Now from D to C, we have V1, and it is in the same direction of the analyzing, so it is positive, V1. From C to A, there is no battery. From A to B, there is no battery. From B to D, there is no battery, so we are finished with the battery. Only one battery in this loop. So the first loop has only one battery. Now put the values. R1 2 and R3 it is 4, B1 it is 5. So here we have 5, I3 into the 4 ohms, I1 into the 2 ohms. Here we have the second equation. For the third equation, we go to loop number 2, and the graph suggests that the direction of analyzing is counterclockwise. This is the new analyzing track, which is cycle number 2 or loop number 2. Now Kirchhoff voltage rule on this loop counterclockwise. I will start from F, it's easier for me. F, E, A, B, F. F, E, A, B, F. Again, it is the summation of IR equals summation of BEMF. First, let us search for the current. From FE, the current is I2, but there is no resistance between F and D, so there is no potential drop here. But from E to A, if you continue, from E to A, we have a resistance 3 ohm and the current of I2. And the I2 is in the same direction of the analyzing in this one. So it is positive, I2 times R2. So here I have I2, R2, and it is positive. Plus, if you go further, from A to B, there is a current I3 into R3, and it is in the same direction of the analyzing. The analyzing is down from A to B, and the current I3 is down from A to B. So it is positive, and it is going into R3. So I3, R3. Continue your loop from B to F. There is no resistance. There is a current, it is I2, but there is no resistance. Here we have a current I2, but no resistance. Now we are finished with the current and the resistance, or we are finished with the potential drop. Now for the increasing the potential across the batteries, from F to E we have a battery of V2, and I am going from F to E in the analyzing process here, and I found that the battery is with me. It is increasing in the voltage, so it is positive. So put here V2. If you go around the loop, there is no other battery here. Only one, which is V2, and it is in the same direction of the analyzing. So we have here V2. I2 times R2. How much is R2? It is 3 ohms plus I3 into the resistance for I3. It is 4 ohm. This is the resistance, 4 ohm. And V2 is 12 volts. And this is the third equation. Now we are at the very important step, is to put our equations together in some matrix or some identity or determinant, as you wish to say. I1 plus I2 minus I3 equals 0. This is the first equation. So equation number 1, I1 plus I2 minus I3 equals 0. What are the coefficients of these? If you put here I1, I2, I3, and the answer of the equation is here. The coefficient of I1 here, it is 1. So put 1. Here the coefficient of I2, it is also 1. And the coefficient of I3, it is minus 1. And the answer is 0. This is from the first equation. These are the factors from the first equation. Now let us put the second equation. The second equation tells us that 2I1, equation number 2 says that 2I1 plus 4I3 equals to 5. Now, first coefficient is 2 for I1. So put it in our determinant under I1. So here we have 2. The second number 4, coefficient 4, it is for I3. So for I3, I'll put 4. Here for I3, 4. And this one, it is the answer. So it is at the last column. We finished with this equation, but there is no value for no factor for I2, so I will put 0. Now go to the third equation, equation number 3. It says that 3I2 plus 4I3 equals 12. Now the first factor 3, it is for I2. So I will put it in the column of I2. I'll put here 3. The factor 4, it is the factor for I3. So I put it in the column of I3. Here, 4. And the 12 is the answer for this equation. We are finished with the equation without any factor for I1, so I put it as 0. Then go to your calculator or use any technique to solve these three questions. To find I1 and I2, I3. Use the calculator mode 5, then two, and put your values. I'll put them and I will come back. Try to make it by your own. I found that I1 equals minus 0.5 amperes. It's okay for the value. I1, it is 0.5 ampere, but because it is negative here from the equation, so the direction of it is not from A to AB. We name this C and D and E and F. Okay. In the drawing, we put it from C to A, but as the answer it is negative, so our assumption for the direction is wrong. So, but it is from not C to A, is from A to C, to the left. Then to the left through R1. Now for I2, I have the value of 2. So it is okay. It is in the same direction suggested by the graph. So it is from E to A, I mean to the left in R2. Now I3, it is 1.5 ampere and it is also positive. So the assumption for the direction is correct for I3. It is from A to B, from A to B, down along R3. These are the three currents. The first part, find the current passes through V1, means I1. I found that I1, it is in the diagram from D to C, but it should be from C to D. So make a correction here for the direction I1 to the left, then it will go down. So I through the V1 supply is 0.5 ampere down the battery or against the battery. Against, better to say like this, against the EMF of the battery. Okay, from C to D. This is part A. Part B, the question asked me to find potential difference from A to B. You can find the potential difference from A to B in any of the branches you want. You can go from A to C to D, then to B. This is some choice. Another choice from A to E to F to P. But the easiest one is from A to B immediately through R3, which is I will follow. Sigma VMF minus sigma I R equals V A B. Now, from A to B, by Kirchhoff, we used to put here 0. Okay, if you go for a closed loop, but when I am going from A to B, it is not a closed loop, so I will put delta V A B. It's not 0. Now, from A to B, there is no resistance, minus. Now, the current from A to B, it is I3. And I am going from A to B, so it is positive, times R3 equals B minus BA. So my path always from starting to the end, from A to B. The potential difference from B to A. Okay. Minus I3, it is 1.5, and its resistor is R, which is 4. VBA delta VAB, which is minus 6. What is the meaning of minus 6? VB minus VA equals minus 6. That means voltage of A is larger than voltage of B. To become negative, this VA should be larger than VB. So, which is coincide or match with our result, because the current is flowing from A to B, so A at higher voltage, B at lower voltage. But don't forget how to apply this equation. You analyze from the beginning, this is the beginning, to the end. The end is B. So go from A to B. While analyzing, go from A to B and put the potential difference from B to A, VBA. So the analyzing from A to B, but the potential difference, it is VB minus VA. Okay? I think it's obvious or clear. Okay. Now, part 3, compare the power of dissipation energy in the circuit with the power of delivering energy to it. Show your work. This is a very important question. Ask yourself, who produces energy in the circuit? The trivial answer for this question, every person said the first battery V1 and the second battery V2, they are the supplier, and the dissipator is R1, R2, R3, which is wrong. Why? The current through V1, it is against V1. V1 increasing the voltage, while I1 going from higher to lower. So it is opposite to the battery. So battery V1, it is in charging mode. So it dissipating energy. The only source for the energy in this equation is V2. When I do the calculation, you will believe me. Let us do the calculations. Element I, R, delta V, P. Now we have three elements V1, R1, three resistors, sorry, R2, R3, and two power supplies V1 and V2, sorry. What is the current flowing through V1? It is I1, which is 0.5. Through R1, it is also I1. Through R2, it is I2, which is 2. Through R3, it is I3, which is 1.5. You can go back to the solution before. And through I2, it is I2 through V2, it's 2 amperes. So here it is ampere, here ohm, here volt, here watt. Now, the first battery, there is no resistance, and the second, resistance. R1, let me go back. R1 is 2, R2, 3, R3, 4. So R1 is 2, R2 is 3, R3 is 4. Now the potential difference through the first battery, it is 5, V1 5 and V2 12, I think, yes. This is 12. I1 0.5 times 2, which is 1. I2, the voltage, I2 R2, 2 times 3, which is 6. I3, 1.5 times 4, it is 6. Now, you can find the power. You can use anything for the resistance, I squared R, or V squared over R, or simply I times V, but V for the same resistance. For the power supply EMF, use only IVV. Don't use anything with R, because there is no R for the power supply right now. Now, for the first one, I times V, 1.5 times 5, it's 2.5. For the R1, 0.5 times 1 is 0.5. 2 times 6, 12. 1.5 times 6, 9. 2 times 12, 24. Now, if you add the power for the resistors only, 9 plus 21 plus 12, it's 21.5. 21.5. If you add the two power supplies, 2.5 with 24, it is 26.5. This is a contradiction to the energy conservation. Why? Because I mentioned before, R1 is in charging process, so it is consuming energy. So the dissipation is due these four. These are dissipator of energy. And this one is the only supply. So you cannot name V1 as a supply. It is a consumer. It is dissipator. Here 24. If you add all of these, 2.5 plus 5, it is 3. Plus 12, it is 15. Plus 9, it is 24. Okay? So for the answer to this question, compare the power of dissipation energy in the circuit with the power of delivering energy. They are the same. And don't forget that be in charging mode. V1, it is from D to C, the current through it from C to D. The current against V, so it is charging, it is not a supplier. Another question, question 2, it's in your book. In the circuit in the figure, there are 3 identical resistors, R1, R2, R3. The switch S is initially open. When the switch is closed, what happens to the current flowing in R1? This is a tricky question again. Let us name the corners and the junctions. A, B, C, D, E, F. Now, from the battery all the way to C, there is no resistor. And from the other side, from the battery all the way to D, there is no resistor. So the VEMF equals delta V AB, and it is the same as delta V CD, because A and C are the same point, B and D are the same point, since there is no resistor here. If there is any resistor here, we cannot say that. Okay? So we say that VA equals VC and VB equals VD because there is no resistance between these points. Now, this is if the switch is open. Now, if the switch is closed, nothing will happen to this fact. VEMF equals delta VAB equals delta VCD. Since VCD doesn't change, then the current between D and C will not change. That's it. So here, no change in current. When this current is changed, if there is a resistor here or here or here or here or anywhere else, if there is any resistance between the power supply and the connection CD, any switching will change the current in the circuit and in the branch. But for this, no change. It's enough for this part. See you in the next part. And we will discuss the Wheatstone bridge and some ideas on Kirchhoff. Assalamu alaikum.
I hope that this video has enriched you more. In the description box below, there are links to both a PDF document for answers and the other videos in this series. This is the end of part 5. See you in part 6. Salam.